I'm going to skip a good portion of this sheet right now. So notice in the top half, step number 2 gives you Q equals MC delta T. Well, we just worked with that a little while ago. It gives you mass equals, Q equals M times heat of fusion or heat of vaporization. We just did that as well. So there's a lot of information on this sheet, including about 2/3 of the way down, it gives you constants for water. Water specific heat capacity is 4.184 joules per gram degree Celsius. You used that at the lab bench a little while back. Specific heat of ice. If you're in the ice state of matter, it absorbs heat differently. Same of steam, the gas version. Lastly, here's the heat of fusion and vaporization. Kilojoules per mole or joules per gram. So I did a little conversion, hopefully make life easier for you. You do not have to memorize any of these values. They will be given to you. Your goal is to know when and how to use them. What we're going to do with the last 20 minutes of class is go over this practice problem right here. So at the very bottom of the page, it says, if you were given 10 grams of ice at negative 10 degrees Celsius, calculate the amount of energy needed to raise the temperature to 110 degrees Celsius. So in other words, we're taking solid ice and we're going to heat it up. It's going to melt into a liquid and we're going to heat it up some more until it evaporates off into a gas. So steam, water vapor. Notice on the bottom of your sheet, I give you 6 different steps needed in order to solve this. In order to solve this, I want you to go to the back side of your sheet, which is blank right now. Again, I'm moving on to the Smart Notebook for this, but here in the middle is the original question. I'm going to show you step by step how to do this, and your homework is going to be basically doing the same types of problems. First off, I want you to draw a heating cooling curve somewhere on your sheet. It's very common and highly recommended that you draw out a heating cooling curve. Now, the things that I want to include is my starting temperature, negative 10 degrees Celsius. You notice how it's on that first slope, because that first slope of a heating cooling curve is the solid state of matter. I also want to include my final temperature, 110 degrees Celsius, on the last slope on the upper right-hand side. The reason why I want to include this when I do my calculation. The number one mistake students make when they do a thermal math calculation is they treat it as a one-step problem. They do Q equals MC delta T. Remember, delta T is the change in temperature. And they just say the change in temperature is 120 degrees Celsius. But not only are we heating up substances, again, heating up would be, I have solid, I need to heat it up here. I have liquid, I need to heat it up here. I have a gas, I need to heat it up here. Not only are we heating it up, we also are going through phase changes. A phase change, the temperature doesn't change, but you're still adding heat to try to break it apart. Going from a solid to a liquid means you're loosening up those forces that hold it together. Going from a liquid to a gas means you're completely breaking things apart. So by showing you this first, what that shows me is I have one step right here, 2 steps, 3 steps, 4 steps, 5 steps needed to solve this problem, which is why you have the entire back side of your sheet of paper to do this with. Part A. Part A is we're going to take our 10 grams of ice from that problem and heat it from negative 10 degrees Celsius to 0 degrees Celsius. Whenever there's a change in temperature, I'm going to use Q equals MC delta T. So what I'd like you to do on the back side of your sheet of paper is start off with Q equals MC delta T. What's the mass of the ice given to us in this problem? 10 grams. The C value, the specific heat capacity, that measurement of how well does it absorb heat before its temperature changes. For solid ice, that value is 2.03 joules per gram degree Celsius. You do not have to memorize that value. It's given to you on the front side of your sheet of paper, which I would recommend hanging on to this sheet of paper when you do the homework, because the homework I didn't put all the constants on it, because it's all on this sheet of paper. Delta T, change in temperature. I don't think you need to show this work. I think you can do final minus initial in your head and know that that's 10-degree change. In order to help you out with this process, I did the multiplication for you. You can see the final answer is 203 joules. Some people ask, why did I underline this 0 and 203 joules? I'm trying to keep track of sig digs. I should only have 2 sig digs in my answer, because if I wrote this 10 correctly, it would have had a decimal after it, so 2 digits, 2 digits, 3 digits. What you're going to find, though, is we're a little bit lenient on sig digs with thermal math, and I'll explain that as our last step approaches. What we just did was we calculated how much energy it takes to go from negative 10 degrees Celsius to 0 degrees Celsius. Why did I choose 0 degrees Celsius? Because that's the last temperature it can exist as a solid. That's my first step. That's my first straight line. Now that I'm right here at 0 degrees Celsius as a solid, step 2, or part B, is melting. Temperature doesn't change in the process of melting. That's where I have to use instead heat of fusion. So part B, Q equals the mass times the heat of fusion. This is what we just did on that sheet prior to this practice here. 10 grams is still the mass of the water. It's always 10 grams. Doesn't matter what state of matter it's in. One of the things I tried to do on this sheet is report the heat of fusion in a value that gives you joules as your final answer. Unlike kilojoules per mole, where you'd have to convert your grams into moles and then you get a kilojoule value, I tried to make life easier for you by giving you 334 joules per gram. Underneath my final answer, you can see that I made a statement that melting just means you're breaking it apart from its rigid structure. I like to use the analogy of you guys in your desks right now are like a solid state of matter. You're in a fixed position, but you're vibrating about. When we were at the lab benches, we were more like a liquid. We were free to kind of move around each other a little bit more. When that bell rings at 9:40, we're a gas. We all disperse elsewhere. So Jackson, let you have that statement. So, this is step 2. Again, I'm sorry if I'm going a little fast. But what we did in step 1 was we took our solid ice. We found out how much energy does it take to melt, or to increase its temperature. Step 2, how much energy does it need to melt? Now we're at a liquid state of matter at 0 degrees Celsius. Step 3 is climbing this slope to 100 degrees Celsius, the last temperature water can exist. So step 3, 10 grams of water from 0 to 100 degrees Celsius. Since there's a temperature change, this goes back to Q equals MC delta T. Notice I put big blue boxes over the top. I'd like you to take a second here to solve that equation. So plug in your numbers. What's the mass of water? What's the C value of liquid water? Look back at the front page to see what that value is, because you don't have to memorize that. And then what's the change in temperature? Delta T. So give you about 30 seconds to see if you can solve that. And then I will reveal the answer. Hopefully you realize the change in temperature is 100 degrees. And the coldest temperature liquid water can exist is 0 degrees Celsius. The warmest is 100 degrees Celsius. Then if I plug that 100 into my equation, C value of liquid water is 4.184 joules per gram degree Celsius. I get 4,184 joules is my answer. Underneath the calculation, I leave a little note that this C value is higher because liquid water is really good at absorbing heat. Again, it's something I discussed with my students a fair amount on one of those last days. Quite frankly, that's one of the reasons why your body temperature is able to regulate itself pretty well, is that high heat capacity of liquid water. If I flip back to my graph, we have just solved part A, how much heat is needed to heat up our solid. Part B, how much heat is needed to melt our solid, turn into a liquid. Part C, how much heat is needed to heat up our liquid to 100 degrees Celsius. Next, we have part D, how much energy is needed to boil our solid, to make it go from, our liquid, to go from a liquid to a gas. "10 grams of water boil." I'm going to take the mass times the heat of vaporization. Once again, I will allow you to plug in the numbers for that step. Look on the front side of your sheet of paper to determine what is the heat of vaporization of water. And I know I give it to you in different values. I would suggest taking the joule per gram value, because everything we've solved for so far is in joules. As you're doing that, I'll just read the statement I have at the bottom of that page. It says the heat of vaporization value that you're looking up is a much larger number than the heat of fusion. Because when you vaporize, you are breaking all intermolecular forces. There is no attraction when it's gases. When you go from a solid to a liquid, heat of fusion, you're just loosening things up. Big value, 22,000 plus joules. It takes a lot of energy to boil something, to vaporize something, to make it go from a liquid to a gas, to break apart, in this case, hydrogen bonding. I know I keep on coming back to this, but we really want to emphasize that this is a multiple-step approach. And too often students treat this as a one-step problem. What we have done in part A is we've figured out how much energy is needed to heat up our solid to 0 degrees Celsius, the last temperature water can exist as a solid. Part B, how much energy is needed to melt the solid to turn into a liquid at 0 degrees Celsius. Part C, heat up our liquid to 100. Part D, boil our liquid, turn it into a gas. Our last step is to heat our gas from 100 to 110. Whenever there's a temperature change involved, the slopes on our graph, we use Q equals MC delta T. So, part E, let's take our 10 grams of water at 100 degrees Celsius and heat it up to 110. So take a minute to figure out your delta T, what's the change in temperature, and then solve for Q. And my only reminder on this slide is to make sure to use the C value for steam. So look on the front side to find the correct value. Today we are doing a fair amount of math, however, it is all algebra. Know what number to plug in when, and you'll be perfectly fine. And our change in temperature should have been 10 degrees. I have 199 joules is my answer there. Very last step of this problem. As you can see on this slide, I'm showing how much did I solve for in each part. In order to figure out the total amount of energy needed to make this happen from -10 all the way to 110, we add it all up. Now, here's my disclaimer for this. The rules of multiply and divide when it comes to sig digs is one that we cover a lot in Chem 1. The rules of adding and subtracting, like we're adding right here all these values, that is not one that we emphasize as much. The rules of adding and subtracting say, what place do they have in common last if I were to do the other steps? We are going to simplify sig digs for thermal chemistry for you and simply say, why not just round to the ones place? Now, if you want to report it in kilojoules instead, you can, but you don't have to. I do show what the value would be if I took sig digs into account on the far right-hand side, but we have deemed that learning thermal math, I think, is enough. To add on to that rules of sig digs, which, especially when we get to adding and subtracting, are a little confusing, let's just avoid that. So, I add up those values. What I can tell you for your homework for tonight, you will have a couple of problems that are multiple steps like this. What I can also tell you is when it comes time for a quiz or a test, we are not going to give you a 5-step problem. Because look how much work that took for you to do that. I'd be testing you for 15 minutes just to solve one problem. It doesn't make sense. We usually do like a 3-step problem. A few reminders I have. Whenever you do this, map it out. Start and finish. However many twists and turns you do on that graph tells you how many steps you have to make. Second one, a reminder, sig digs. We are going to be relaxed on sig digs for thermal chemistry. Lastly, number 3, what we just did here was how much energy do you put in to heat something up? We can do the exact opposite. How much energy is needed to cool something down? If you cool something down, like you just saw in the lab at the start of class, your delta T should always be a negative value. Right? Negative means exothermic heat's released. What I say for number 3 is we should also make the H values negative. So for example, if I go back up to my heat of vaporization, to go from a liquid to a gas, it would take 2,263 joules per gram. But if I was going gas to a liquid, I'd have to cool it off. I'd have to lose heat. That'd be a negative 2,263. Okay?